Sound waves are produced by some source moving back and forth and creating regions of compression and rarefaction in a medium. A medium can be air, it doesn't have to be. It could be water, it could be some solid material. So sound waves are longitudinal. That's because they have back and forth motion in the direction that they're moving. Now, in principle, this motion could occur at any rate. It could happen, you could have sound waves being generated by a source moving back and forth one time every century, or it could be moving back and forth 100 trillion times per second. Those could be sound waves. But the human ear only hears sound waves that have frequencies between 20 hertz, or 20 cycles per second, and 20,000 hertz. So human hearing goes between 20 hertz to 20 kilohertz. Well, that's what they always tell you in textbooks. In reality, 20 hertz is pretty low, and if you play that sound loud, you'll probably feel it more than you'll hear it. It's more just like a rumbling that you'll feel in your chest rather than a distinct pitch. And 20 kilohertz is super high frequency, and you probably can't hear it. Most adults, their range of hearing starts to decrease when they're even in their teenage years, and as you get older and older, this number goes down. So if you're in your 20s, this might be something like 17 kilohertz. You can hear up to 16 to 18 maybe. So this is kind of an idealized range, but this is generally what people will measure when they're testing audio equipment. If you ever buy good headphones or something like that, they'll probably show a graph of how the headphones respond through all these frequencies. So these are known as audible sound waves. If you have frequencies lower than 20 hertz, that's known as infrasonic. And frequencies above 20 kilohertz are ultrasonic. You might have heard of ultrasound. That's because you can use high frequency sound waves for some interesting applications. There's several medical applications in imaging, where you can image the fetus in the womb. You can also use them to perform kind of non-invasive surgeries or destroy tissues or tumors without having to cut through the skin. Ultrasound is produced by connecting an alternating voltage source to a material called a piezoelectric. This is a material that shrinks or expands in response to an electric current. So it changes size. So if you send an alternating current into a piezoelectric material, it will expand and contract, which makes it a sound source. And you can send a pretty high frequency current in there and it'll shake more rapidly than 20 kilohertz. And that's how ultrasound is generally produced. Interestingly, with piezoelectrics, the inverse is also true. It will produce an electric current in response to its size changing. And its size changes when sound waves hit it. And that's useful for making detectors. Piezoelectrics can detect sound waves. You can use them as microphones. As the sound wave hits that material, it will shrink or expand, depending on whether it's getting the compression part of the sound wave or the rarefaction part of the sound wave. And it generates an electric current that then you can convert into an audio signal. Some other applications of ultrasound, like I said, you can image the fetus in the womb. You can use this for non-invasive surgeries. There's the Cavitron Ultrasonic Surgical Aspirator, or CUSA. It's used to treat brain tumors. You can use ultrasound to destroy kidney stones. And another application that we usually use in Physics 6, which we didn't get to do this semester because we're not meeting in person, is motion sensors, motion detectors. When we did the first couple labs measuring position and velocity and acceleration, in a physical class we would use a motion sensor that produces ultrasound pulses, and those measure distance. All right, so there's some characteristics and applications of sound waves. Next, we'll talk about the speed of sound.